Hi, I'm Oliver Gao. I'm the director of Cornell System Engineering Program, and I have been very fortunate to conduct what I call these system conversations with the great minds that we bring to Cornell for our Ezra seminar series. So today, I'm very delighted and honored to be talking with Dr. Yaniv Mordecai. Actually, he is a senior research scientist at Amazon and also a senior teaching fellow at Tel-Aviv University. He was a Technion MIT postdoctoral fellow at the MIT's Engineering Systems Lab back in 2019 to 2021. He holds his Ph.D. in system engineering, and also before that, he did his master's and a bachelor degree in industrial engineering and also operations research. So actually, Yaniv, he has over 23 years of experience in industry, government, and also academia. His research interests include applications of artificial intelligence in complex systems, operation research, model-based systems engineering, and also cyber-physical informatics. I think that's really so exciting, all the hot topic areas. So Yaniv, it's great to have you here.
It's great to be here. Thank you for inviting me.
Thank you
for a big honor.
Well, thank you for taking time to visit with us. So, as I was briefly talking to you, I'm really excited because in my view, I have to acknowledge myself. I don't think I'm a full true system engineer because my background starting civil and environmental engineering, and my interest in system engineering got developed after I started my teaching career, because my research covers transportation, environment, and public health. That is a complex system that got me into system engineering. However, Yaniv, your training, your education, and all your work, as always, you rooted from system engineering has been really expanding in system engineering. So please tell us more about how your journey in system engineering.
Yeah, definitely. So first of all, I wasn't born a systems engineer either. I also it's very interesting actually. I was originally, as you mentioned, I studied industrial engineering, and I was majoring mostly in information systems. Mm-hmm. And as part of one of the earliest roles I did, so I was in Israel, we have what we call the academic reserve. So you actually go and study a bachelor's degree, sometimes also a master's degree, and then you're getting recruited into the military, and then you serve as an officer in the military in your capacity as an engineer. Mm-hmm. And of course, when I got to the the military, I started seeing all these different problems that I felt I might be able to solve, but I didn't yet have the tools or the knowledge or the understanding. And at first, I was tackling some of these problems through the paradigm or perspective of project management, mm-hmm. which was something that was more we were more familiar with coming from the background of industrial engineering and management. While I was working on project management processes, mainly to streamline the entire project generation pipeline, I was also noticing that there is a lot of complexity involved that comes from the complexity both of the organization and its operations on the one hand, mm-hmm. and the systems and technologies that we're building or integrating into our operations on the other hand. And then I realized that this is what we call systems engineering, right? I mean, yes. Trying to see, I would say, when I'm thinking about OR versus systems and operations research versus systems engineering, it's almost like looking at the apples versus looking at the tree, right? So when you're in doing operations research, you're looking at the apples. You're trying to optimize for the number, for the quality, for the color, and so on of the apples. And when you're looking at systems, and you're looking at the tree, because that's the system that generates everything. And if you scale it one level up, you'll be looking at the entire orchard or the forest. Uh-huh. Right? In operations research, whereas in systems engineering, whereas in operations research, you'll be looking at the individual tree. or the set of individual trees. And I realized that I need to understand what is systems engineering. I started going into these in cozy meetings. Israel also has a in cozy chapter that has been running for a long while. I think the first time I actually heard about it was when they were presenting a seminar or kind of an open day on requirements management tools. And I said, requirements management sounds interesting. What is that? And I went to, there was this meeting and all of a sudden, so all these engineers from all sorts of disciplines, all trying to figure out something that is not particularly related to any discipline, right? It's not industrial engineering, it's not software engineering, it's not electrical engineering, it's not mechanical engineering, aerospace engineering. It's relevant to all, basically. And I start to learn and understand what does it mean. And I also realized and I learned at the time that what we were doing for software modeling was also becoming of interest to the systems community. So everything was kind of coming together, and I realized that what I was mainly after is solving problems in the domain of systems engineering, not necessarily the project management, the process of getting the program up and running, but more around the technological or the socio-technical complexity of developing these systems, right? I mean, the technology and how it fits into our operations was much more of a challenge than figuring out, the headcount or the budget or things that pertain more to the project management perspective. And I'm not saying that these are not important by any mean. I'm just saying that the way I was looking at it was more from like, how do you solve the problem from the architectural level, not necessarily from the programmatic level.
Yes.
And of course, there is an interaction between the two. Fast forward, when I started my master's, my master's was actually still in operations research because I was still very much attracted to this domain, and I felt like it would be interesting to explore and study a problem in that had to do with game theory and optimization. And when my advisor asked me to bring in an example or a problem from my field, from my area, the idea that came to mind was a systems project, right? A massive helicopter upgrade project that I was working on at the time, and not necessarily from a systems engineer perspective, but still with a little bit of systems engineering in mind. And I was working on this research. I was working mainly on aspects of risk analysis. So risk analysis is maybe one of these areas that connects operations research and decision analysis on the one hand with systems engineering on the other hand, because it pertains both to the programmatic aspects and the technical aspects. When we're talking about risk, we're talking about the objectives of the program that might suffer from any sort of risk materializing. It could be the budget, could be the schedule, could be the performance of the system. So when you look at the trade-offs between all of these, then you realize that if you're just approaching from a project management perspective, or if you're just approaching from a technical perspective, you're not necessarily capable of capturing all these interactions. And there I saw that systems engineering could be a good way to solve this. And I did find, of course, that risk management and risk analysis is one of the key pillars of systems engineering. And I was working in that space for a while. I was also working on modeling, and then I happened to sit in a seminar of my Ph.D. advisor, not yet to be Ph.D. advisor at the time, Professor Dov Dori from Technion, where he presented his modeling approach, object process methodology, which I immediately felt like a natural continuation of work that I did in modeling for risk networks, risk graph set as part of my master's. And I realized that I need a language that will help me bring together the, let's say, analytical constructs that were representing the processes or the behaviors of the that we're analyzing on the operations research side of things, with how all of these things actually fit into the architecture of the system at the end of the day. And I felt like this was the perfect way to represent the concepts or the conceptual processes both within the system and surrounding the system, right?
And Dor, he pioneered this subject area.
He was definitely one of the pioneers in the field, and his thoughts on modeling and simulation were coming together just around the same time as the OMG was forming. And it's interesting. He once told me the story. He actually came to this from the problem of document understanding and image understanding. So he was all around algorithms for computer vision and pattern recognition for identifying. And he said, okay, now that we understand the image, how can we formulate it much better, right? Or at all? And then he went and started building this approach of his that consolidates the structure and behavior into one unified representation.
Wonderful. Sorry, I distracted. You were talking about, you were trying to find it kind of combine its architecture and also the analytical. And then you came to Dor, and then you started working with him.
Yeah. And the first thing I was trying to work on actually was to build risk management models and risk mitigation models for complex systems that would take the risk analysis and decision analysis methodology and fit it on top of and within the system of interest. So the idea was that when you come up, let's say you identify a risk, okay, that something might break or fail in your system, right? So you end up with, if you're just coming from a pure risk analysis perspective, you might end up with a task, with a project management, risk management perspective, you'll end up with a task in your project schedule to fix the problem or to mitigate the problem. But you also need to show how it fits into the architecture. Like if you're going to integrate a risk mitigation mechanism or some sort of protection mechanism or prevention mechanism into your system, it will interact with the rest of your architecture. So you need to be able to show from both sides, right? Both from the programmatic side and from the architectural side, how this gets resolved. And then I realized that when we're building system models, that's how my research gradually shifted. When we're building system models, we're often focusing on the nominal sunny day scenarios, on what is the common understanding of how the system should behave or will behave, rather than on all these anomalies, exceptions, off what we call off nominal situations and scenarios in the system that make up probably 80% of the complexity of the system that we need to deal with. So that's how I started focusing, instead of on the nominal aspects of the system, on the off nominal, on the disruptive aspects of the system. And we started exploring all these different phenomena. And we one thing that really caught my attention was something that we call the cyber-physical gap. So it actually started pretty boring task that we were asked by Professor Dori, me and a colleague of mine who was also doing his doctorate at the time on airport systems engineering. We were asked to come up with a model for passenger incoming or outgoing passenger at the airport, and from a systems perspective, right? So we started building the model, and we realized that when we got to the baggage part of things, right? I said, okay, what if the baggage doesn't show up? And then we realized that
off normal case.
Yes, that's an off normal case. And we realized that there is this duality that if you think about it, duality of the existence of entities that which is both in physical space, right? So there's a glass of water here, right? Or my luggage, basically, right? And then there's the informatical representation of these entities in the system. And I realized that this is giving rise to this potential mismatch where the behavior of the system is based on its internal representation of the external environment, including my luggage, right?
Yes.
And then there's the external luggage. So when your luggage doesn't show up on the carousel at the airport, it's not because the baggage is lost, quote unquote. It's because you or the system that manages the baggage doesn't know where the item is. Mm-hmm. The item is somewhere, unless somebody opened the door and threw it above the ocean, right? But in most cases, let's say, it's just a matter of knowing where the item is.
That's a gap.
And that's the cyber-physical gap,
Yes.
the difference between what the system knows about the environment and the actual situation of the environment. And we went and studied this a little bit deeper and understood this problem is just across the board. And one very famous example that we realized was actually a manifestation of cyber-physical gap was the 3 Mile Island nuclear reactor accident in 1979, if I'm not mistaken, in Pennsylvania. And the problem there was that, if I can articulate it correctly, there was a situation where the control room was not aware of the fact that a valve was stuck open, and they were thinking that the valve was closed, and that's why they were also stopping the water flow into the reactor, causing basically coolant starvation, overheating of the reactor, and exposure of the top of the reactor, which also caused the partial nuclear meltdown, partial nuclear reaction, and you know the impact and the consequences of that accident were not really clear for a long time. Actually, people thought that the accident was contained, although it was considered the worst accident in nuclear power industry in the U.S. But the whole point was that this was a cyber-physical gap, because the failure of the control room to know the actual situation of the valve resulted in making wrong decisions that impacted the system itself. And of course, we saw that later on in many other cases. I analyzed the disappearance of the Malaysia Airlines 370 flight from Malaysia to Beijing in 2014 as a cyber-physical gap, where it was actually more than just a cyber-physical, it was an exploitation of a cyber-physical gap
That's right.
by the pilot. And we also saw, for example, that one of the main consequences or decisions following that disappearance of the airplane was the transition from point-based operations in air traffic control to trajectory-based operations in air traffic control. So that the idea was that you also need to know where the plane is coming from and where it's heading to, so that you'll be able to make sure that it is on the trajectory in which it's destined or supposed to keep flying, and that it's not, making all these weird decisions in midair without any relation to where it was supposed to fly. And so you see how these complex phenomena are both they require both analytics and systems perspective, right? Yes. And that's, I think, how I kind of started working as both an systems analyst or algorithm person on the one hand, and as a system architect on the other hand, right?
Yeah,
so
a system thinker.
Yeah. So you exactly. So you have to understand. Sometimes you just have to build something. So you have to design. You have to understand how things work. What's the functions? What's the input? What's the output? But then once you realize that, you have to start seeing where do you cause your system to fail, or where could your system fail. And again, you're not building it for meeting the sunny day scenario, which is 20% of the time. It's for all these unique situations where the system will not actually or may not actually fill its role or its function. And then you need more than just the ability to see an architecture and a flow of information or flow of material, for example, or energy. You need more than that. And that's how I always sought for the... I went to the modeling aspect because I always felt that it would be easier to build any analytical process on top of the core system architecture model. So I have a system architecture model, and then I can analyze it and enrich it with insight that's coming from the various analysis processes that I can run on top of it. Risk analysis, decision analysis, configuration analysis, scenario analysis, all these different things. So that's how I always converge back into the modeling paradigm as kind of the bringing in the authoritative source of truth for the model, rather than having all these different disparate models that were useful enough themselves. So, for example, take decision trees, right? So when I studied decision trees, I always felt, how do I implement or integrate decision trees into the architecture model, right? That was always somewhat of a challenge, because the decision tree is behaving as a separate entity, right? And then when you have to integrate the decision process itself into the system that actually makes the decision, whether it's a human decision or an automatic decision or a semi-automated decision, that how do you build that into the architecture model? There's no good constructs for that. And I kept seeing that working with conceptual modeling, like with OPM, we could actually describe a lot of these processes and how they fit into the system. Similar would be fault tree analysis, right? I mean, fault tree analysis is also something you would probably do outside of the main system model. But then how do you integrate the fault tree analysis into the behavior of the components, right?
Yeah.
And how do you show that the behavior of the components could result in the failure that is represented in the fault tree? So I was always trying to come up with ways to integrate models and integrate representations. And at some point I realized, and that I think maybe brings me more towards the kind of research, right? At some point I realized that the way to solve these problems may not necessarily be by trying to kind of bring in all the different representations into a single model, but rather to create a data representation that is robust enough to accommodate all these different system representations, whether they refer to the architecture, whether they refer to the analysis processes, and so on. So, and that's where I started studying or try to understand how graph theory and graph-based algorithms could be useful in getting to a more primitive and yet more robust representation that covers not only... So when we're thinking about graph theory, it's often synonymous with network analysis. But when you deal with complex system models, it's not enough just to connect the different nodes. There's also a lot of semantics layers that go on top of that. For example, classification of or specification of attributes, right? Or specification of behaviors, or aggregation, or let's say decomposition, which is architectural, structural on the one hand, and behavioral, functional on the other hand, and how these two hierarchies interact with each other. So graphs in that regard don't represent only nodes and the connections between them, but also, I would say more broadly, concepts and the connections between them. And when you deal with concepts and the relations between them, you start thinking about ontologies, and very quickly you get to the need for a formal representation or formal theory that captures the analysis of these ontologies. And that's how I came to study category theory.
Yes.
And all these things started coming together, right? I mean, the ability to use category theory as a as kind of an abstract mathematical representation of concepts and relations among them, and it was interacting very nicely with OPM's ontology, which is also very basic and refers to processes and objects, although it's not exactly the same as what the ontology of categories contains. It's slightly different. In categories, we're talking about morphisms and objects, and so processes are not exactly morphisms, and objects are not exactly objects, but still, I mean, the ability to start looking into these different conceptual representations and how, to bridge, to create bridges between them or interfaces was always very interesting, because once you have that, basically you're working in a graph-based environment that lends itself to all the various graph analysis,
The math would come in.
algorithms, all the analytics models that we have from operations research and graph analytics and so on. So it all revolves around the same thing. It's all coming together, I would say, and that I felt for me was very exciting. So I realized that as a systems engineer, or I would say as a systems engineer researcher, okay, you have to be aware. I mean, what type of research can we do in systems engineering? That's the big question, right? And I think this the big questions we need to answer in systems engineering is mostly, for me, about methodologies, right?
Yeah, so I think that's kind of. Thank you, Yaniv. I think that's fabulous. I really, I was taking notes when you were talking about that. I wrote down. You talk about integration, and you talk about data representation, and you talk about from concept to ontology, and of course, you also mentioned the category theory. I think this it seems like it kind of from when you kind of shifted from your master's study to your Ph.D. Like you started kind of really I think get into this system engineering, because I think you were motivated by trying to find a system engineering project, and then you are trying to solve those. But first you talk about the cyber physical gap and all these. But I see it's really started with application stimulated this kind of research, and then it get you and you end to this category theory and graph theory, and then now you connect the graph theory to all the math is the OR thing that you did in your undergrad and in your master study. So with this, as I think you are basically going to start to talk about, right, as now you have built this knowledge base, and I think I honestly say I don't think in this whole world there are many people like you who has this unique knowledge structure, right? It's really tremendous. So with such a unique kind of blessing of all this knowledge, and then of course, as you say, you want to identify as a researcher, you want to identify some key challenges that you would like to address. So in your view, what are some key challenges that you feel you are uniquely positioned to address?
Yeah, that's a big question. Just to kind of finish the thought in that regard, I think that first of all, you're absolutely right. The inspiration is coming from applications. So I would say that in systems, complex systems, the lab is the field. There is no lab, so to speak, in the sense that you have a contained environment like you have in life sciences, for example, or even physics, where you can come up with micro models of the environment and kind of test them out. That you have to have a good connection with the industry where complex systems are actually being built. And a lot of the collaborations we had over the years were with industry. I was working in industry while I was doing my studies, so it gave me inspiration. And I have to say, working or coming from a research perspective inspired me to tackle systems engineering problems in my day-to-day work from a more scientific, rigorous approach, right? Not just try to solve let's say we had to come up with an interface for two components, right? It's not just about solving that. It's about solving for the process of building interfaces between components. Think about it this way. Or for the process of coming up with an integration plan, and not just for coming up with the integration plan itself. So so I think that it's very, very important to have this inspiration and have, be very grounded both in the application and not only in the theory, but also to be able to rise above the day-to-day work that you do in industry and search for these patterns, search for these processes, search for these the methods. And that's why I was mentioning that I think in systems engineering, a lot of the research eventually has to do with methodology, with how we actually build better, faster, I would also say cheaper methods that generate equally good or better results in the systems engineering processes, right? So I always say system requirements, we still have to generate a list of requirements, specifications, and design. We still have to generate. We can't get rid of it. It's not like it's going away. We'll still have to say, somebody will still have to say what the system should look like and what it should do and how it should be designed, right? The question is, are there processes, are there methods, are there mechanisms that can help us do these processes a bit better? And especially since these processes require a lot of creativity, abstract knowledge and abstraction in general, understanding of the of different characteristics and aspects of the system, being able to look at hardware, software, mechanical, materials, humans, right, and think about all these as blocks, right? I mean, this is a level of abstraction that not all people have, not all engineers have, and it's acquired, obviously, right? I mean, again, I wasn't born a system engineer. I just realized that abstraction is what I call abstraction is the key to emergence. If you understand how you can abstract behaviors and components, then it also gives rise to the emergence, to the added value that the system can generate from the synergy of all its components. Only when you're starting to talk about functions and functionalities and behaviors and end-to-end processes is where you can actually start seeing the bigger picture and not just a set of components where every one of them is generating or fulfilling its own function. So I think definitely being able to capture these aspects in a more tangible way is somewhat of a challenge that should definitely be tackled by research. That's why I think, for example, that formalisms like category theory could be very useful in that regard, because they help us represent conceptual structures, both the model itself and in the model itself and in the modeling process. So in the architecture and in the process that drives the architecture, which is a system in and of itself, right? So thinking about processes, thinking about mechanisms, thinking about methods is definitely something I think we can definitely continue investigating and exploring in systems research. And I think the nice thing here is that once you identify a task that you want to improve the performance, right, or the quality of the outcome, right, that you can mount on top of that any sort of technology, any sort of scientific method or approach that would fit. So, for example, today I discussed artificial intelligence, right? I mean, if you understand that you're dealing with a lot of text and you need to extract value from that text or insight from that text, and you need a mechanism that will help you do that, you can integrate mechanisms or technologies like natural language processing and large language models and generative AI and so on to help you get data out of these, to help you get insight out of that. But once you've been able to extract this insight and even to kind of structure it a little bit, right? The next problem you're dealing with is a data science problem, because you already have the data in tables. Now you have to start aggregating it, measuring it, pivoting it. These are data science problems. They're no longer natural language process. So you have to be able to move to a different set of skills. So I think this is a platform where you can integrate various types of knowledge. Even when you're dealing with, for example, cyber physical systems, right? So you have to solve problems that where, let's say, you deploy a configuration for a IoT device or for an electromechanical device. So you need mechanisms that, for example, that involve field programmability, right, for hardware. So you can bring that in as well. So all of a sudden that also becomes part of what you can do as a systems engineer. I feel what is connecting all of these is the ability to implement and execute the algorithms and the mechanisms that you're coming up with on top of or in conjunction with the systems that you're building, right? And then in some sense, these processes themselves become part of the system, right?
Yes.
So the system analysis process is eventually part of the system. And the system setup process is part of the system, right? And I know it may make sense, but when I'm talking to students about these things, they don't often identify these as part of the model, or they don't necessarily specify them as part of the processes in the system, right? And that's why I'm insisting on them understanding what is the system, not just what is a system. And I'm saying, look, there is the system that you are building, but there is also the system that builds this system, right? That's what we call system 1 and system 2. And there's also system 3, which is the system that operates the system that you'll be building, and is also in constant interaction with system 2, which is you guys, where it tells you what it needs and what are its requirements and what are the gaps and so on, and what is it like it's programmatic framework. So understanding all these different layers helps you also understand how information and outcomes and effects are propagated from layer to layer, right? Again, nowadays when you see a lot of modern systems, they are getting built and deployed and operated all at the same time, continuous delivery, continuous integration. So it's no longer a very clear separation between building the system and putting it out there and using it. I mean, think about Tesla, for example, right? They can issue update patches to your car's software,
Yes.
right? While you're driving it, basically, right? I mean, if they need to update the software on the vehicle to solve a bug or a safety hazard, they just do that, right? So the development, the integration, and the operation are all becoming very intertwined, and that in itself is also a very big challenge, right? How do you deal with all these different types of systems and ways of thinking about systems, where they actually start propagating each other and interacting with each other and interfering with each other even.
Yeah, it's it's a self-evolving, like a living system, right? Yeah,
exactly. It starts becoming very much like an organism.
Yeah, exactly.
And obviously that also causes a lot of phenomena that we meet more often in natural systems, like emergence, right? And emergent behavior, and all sorts of situations where the system starts evolving in itself and developing functionality and capability that it didn't necessarily, it wasn't necessarily supposed to own, right? Just because of the ways you can utilize utilize different components of the system. One example I'm giving my students is always that, for example, our mouth, right?
Yes.
Is a dual function component, because it helps us. It's more than dual, because it helps us eat, but it also helps us speak, and it also helps us breathe, right? So all these different functions are being implemented with just one single organ, although none of them is actually exclusively owned by that component. I mean, that component still needs to work with various other components or organs, as we call them in the human body, to achieve all these different functions of breathing, eating, and speaking, right?
Yes.
So you start seeing these types of patterns emerge in complex systems nowadays, and I think that's also a big challenge, that where I think maybe in system science we have not dedicated enough attention to understanding complex phenomena like this, and how they manifest themselves in man-made systems, or systems that contain significant man-made segments.
Yeah, this is wonderful. Thank you for sharing your thoughts, and also your in depth of your research. Of course, you can see that you're talking about really your journey through all the exploration, and you yourself was also a system, again, evolving, right, through this. And then as your system knowledge grow, as an expert in system engineering, by the way, I try not to distract you while you are talking. When you explain, system engineering, the goal is really try to produce, for example, a lot of engineering, when we do engineering, our goal is to engineer a product.
Yep.
Right. However, system engineering, as you may emphasize, it's really the outcome, the product is really a process, an algorithm, or a methodology that can make better things. So you say it's not, the system engineer, the goal, the ultimate goal is not really, okay, just produce a better product. It's really to come out with a better process.
Exactly.
I think that's a concept, I got from you, we were talking about that. Thank you. So with this, all this, with the beauty of system, with importance as well as complexity of system engineering. So, of course, in your talk earlier today, you talk about AI. So, what do you see either the challenge or opportunity? What do you see as the potential interaction between AI and a system engineering and a system engineer as a community? How are we going to be able to best make use of AI?
Yeah, I mean, this is a very big question, and similar to the rest of the questions you're asking, which is good, right? Thought-provoking. And I was trying, again, as you saw in the presentation earlier today, I was trying to find I'm always trying to find ways in which formalisms can work together, right? I mean, the easiest, or more, let's say, straightforward approach would just be, hey, I can just communicate with this sort of robot that gives me answers to my questions, right? And or machine or platform or whatever we call it gives me answers to my questions. Let's just throw away whatever we used to have until now and just make this interaction better and better. And I don't necessarily think that would bring more value. I think that, on the contrary, one of the problems you're seeing when you're going into so when you're talking about the interaction with generative models, you have what we call long and wide, or deep. Okay, so think about our conversation, right? It's you're asking a question, I'm answering, and then you're asking another question, and I'm answering, and maybe I'm asking a question and you're answering. So there's a whole conversation going on here, right? So we can do this conversation with an AI, right? Mm-hmm. Now the thing is that the conversation with AI behaves like a funnel. So it starts with a very big scope,